So what's a noise gain? Noise gain will be discussed with respect to the noise in the operational amplifier circuit when we discuss that topic, I think in chapter number 4 perhaps, most likely yes, chapter number 4, because we're going to discuss noise at different frequencies. But in general, what is noise gain, or what's the effect of the noise gain? Basically, noise gain tells you how the gain of the circuit is going to be affected if you have random noise at different frequencies in the circuit. So the higher your noise gain, the lower value of your closed loop gain is going to be for the specific circuit. As simple as that. And so how do we incorporate noise gain right now in the equation that we have studied so far? That is the equation of the non-ideal closed loop gain, which is this equation. So here we incorporate Kn. Kn is basically, in this equation, 1 over beta. In this equation it is 1 over beta. So non-ideal gain is the ideal gain, closed loop, 1 plus Kn over open loop gain. So observe, if you have a lot of noise in the circuit and your noise gain is high, A is, whatever the value is, 200,000 or whatever you are using in the circuit, higher the value of K, this factor is going to be smaller, Kn over A. And lower the value of K, if noise is not affecting your circuit, lower the value of K, this value is going to be smaller. So if Kn is high, your ACL, non-ideal and ideal are going to be different. Not that much different, but still they will be different. And Kn is going to be low, then ACL non-ideal and ACL ideal will be very close to each other. So noise is not going to affect the gain of the circuit that much. So that's the whole concept of noise gain. Again, as I mentioned, we're going to look at it next chapter to understand it completely. So how do you calculate the noise gain to calculate the non-ideal gain equation, non-ideal gain value of your any amplifier, not just inverting and non-inverting, but any amplifier. So there are 3 steps that you have to go through to calculate the noise gain, and these are the 3 steps. So the first step is you have to de-energize all input voltage sources. All the input voltage sources, you are going to ground them. So right now we're not talking about the bias sources, just the input source that you are connecting to the input terminals of your operation amplifier. We don't even consider bias sources, of course, in our circuit when we are discussing them. So de-energize all input sources, introduce the test source at the non-inverting input of the op amp, and then determine V out over V test, and that will be your noise gain. So let's look at some example and discuss them. The first example is, what are the noise gain of inverting and non-inverting amplifier? So this is your non-inverting amplifier, right? So for the non-inverting amplifier, you had V input. So first we're gonna take V input out, we're gonna ground it. So we're gonna ground this thing, right? De-energize them, and then we're gonna introduce a test voltage source as the non-inverting input. That means basically now we'll remove the ground again and introduce a test input source. So the circuit is not going to change. The non-inverting circuit is not going to change. It will still be the same for the non-inverting circuit. Okay. So since the circuit is not going to change, if you calculate V test over V out, we already know that gain, not V test over V out, sorry, V out over V test, we already know the gain of the non-inverting amplifier is 1 plus RF over RI. So the noise gain for non-inverting amplifier will be the same as the ideal gain equation, which is 1 plus RF over RI. That's how you calculate the non-inverting amplifier. What about the inverting amplifier? Okay. Since I'm not showing you inverting amplifier, I'm just gonna draw it for you. So your inverting amplifier is, of course, negative, positive input output. So that's your RF, that's your RI, and then of course you have ground. Right, that's your inverting input amplifier, inverting amplifier. So to calculate noise gain, first, this is the input voltage. So calculate amplifier, first you're gonna ground the input, right? You're gonna ground the input source. And then you are going to apply a test source at the non-inverting input. So you're going to, I'm going to erase this right here, and then I'm gonna go ahead and then apply a test voltage source over here, VTest. And then I'm going to calculate the gain, V out over VTest. So look at the circuit. The circuit is the same as this, right? The non-inverting amplifier, when we were calculating the noise gain. So the gain of this, the noise gain of this circuit will exactly be the same. Noise gain of this circuit will be this. So the noise gain for both inverting amplifier and non-inverting amplifier will be given by the same equation. However, remember, their closed loop gain is not the same. Closed loop gain of non-inverting amplifier is the same as noise gain, ideal value that is, but the closed loop gain of your inverting amplifier is RF over RI. So it is not the same as the noise gain. So keep that in mind. Don't confuse between the two. Next example, we have a summing amplifier, and we want to find the noise gain. We want to find the actual value of gain of each of the gain associated with each of the input, right? So as you can see here, first we grounded the input, these two input, we grounded them right here, and then this was grounded, right? This is grounded, and then we remove this ground and introduce a test source, right? Now these two resistors, as you can see, they are connected between the ground, and they're connected between this node. You know that the node will have the test value the same as test source value, whatever, but anyway, this is a single node, node A. It's both of these are connected between node A and this. That means they are parallel to each other, so we can replace them by a single resistance using parallel equivalent, and that parallel equivalent will be 8 kilo ohm. So now look at the circuit again. It becomes what? It becomes a non-inverting amplifier. So again, the noise gain for this one, the same noise gain, 1 plus RF over R equivalent. R equivalent, of course, is this. So we calculated the noise gain, which is 16, and then you're gonna go ahead and calculate the actual or exact value associated with gain value associated with each input. So remember, the ideal gain values associated with each input was negative RF over R1 and negative RF over R2. Remember, this is the summing amplifier. What is the gain of the summing amplifier, or what is the output of the summing amplifier? Negative RF over R1 V1 plus RF over R2 V2. Right? So this is the gain associated with the first input. This is the gain associated with the second input. So the exact value of the gain ideal is negative RF over R1, that is negative 10 for A1. Exact value is A1 ideal over 1 plus Kn over A. We calculated Kn to be 16. So the exact value is going to come out to be negative 9.9984. Observe, there's really no difference. Likewise, for the ideal gain value for the second input, negative RF over R2, negative 5, and the exact value is going to be negative 4.992. Again, no difference. So noise gain is important. You're going to see the noise gain in I believe in the next chapter as well. So make sure you understand how to calculate the noise gain for any operational amplifier. You have to go through 3 steps again. First, de-energize the input voltage sources by grounding them. Second, apply a test source at the non-inverting input of the amplifier. And the third, calculate the gain from the output to the test source. And that's going to be your noise gain.